Have you ever wondered, what if your life wasn't the only version of reality? What if, somewhere out there, there's another you living a completely different life, making different choices, following different dreams? Is this just a thought experiment, or could it be real? And if it is, how does that change everything we know about existence? In this journey, we'll dive into the science and philosophy of parallel universes, a concept so vast and mysterious that it might just redefine what we think reality is. Imagine this: somewhere far beyond the limits of our perception, there exists another version of you. Not just one, but countless versions. Perhaps in one reality, you're an artist creating breathtaking masterpieces, and in another, you're an explorer charting the unknown. It sounds like the stuff of science fiction, doesn't it? But what if it's more than just a story? What if the idea of parallel universes isn't fantasy, but a possibility rooted in the very fabric of our universe? For centuries, we've believed that reality is singular, one timeline, one set of events, one you. But the concept of parallel universes challenges that belief entirely. It suggests that reality isn't a single thread, but an endless web with infinite possibilities unfolding simultaneously. Think of flipping a coin, heads or tails. Now imagine a world where both outcomes happen, each in its own universe. It's hard to wrap our minds around, isn't it? But here's the real question: if these universes exist, where are they? Why can't we see them, touch them, or prove they're real? And if they are real, what does that mean for us, for our understanding of existence itself? It's a mind-bending idea, one that forces us to rethink everything we thought we knew about reality. And to truly explore its depth, we must turn to the science, where some of the most extraordinary theories suggest that parallel universes might be more than just a thought experiment. Parallel universes, what do we actually mean by that? Is it one big cosmic duplicate of our world, or something even stranger? The truth is, there's no single answer. Scientists and philosophers alike have explored multiple interpretations of what parallel universes might be, each more fascinating than the last. Let's start with one idea: infinite possibilities. Imagine every choice you've ever made, the roads you've taken, the words you've spoken. Now imagine every choice you didn't make, creating a new universe, a new reality where things turned out differently. Perhaps in one universe you decided to pursue your childhood dream, and in another you took a completely unexpected path. It's like a cosmic version of the choose-your-own-adventure story, where every option leads to a new chapter in an infinite book. Then there's the idea of alternate timelines. Think of history as a single thread running through time. Now imagine that at key moments, pivotal events in history, that thread branches out. What if, in another universe, dinosaurs never went extinct? Or if humanity never discovered fire? Entirely different timelines with outcomes we can't even begin to imagine might be unfolding alongside our own. But here's the twist: these interpretations aren't just philosophical musings. They arise from some of the most intriguing scientific theories. For example, quantum mechanics suggests that every quantum event could split reality into multiple outcomes. In one universe, a particle moves left, in another it moves right. If you follow that idea to its logical conclusion, you end up with a vast, perhaps infinite, multiverse, all springing from the fundamental unpredictability of the quantum world. And what about the cosmic scale? Some scientists propose that our universe is just one bubble in a vast cosmic foam. Countless universes existing independently, each with its own set of physical laws. Imagine floating in an ocean, where every bubble holds a completely different world. So whether it's infinite possibilities, alternate timelines, or entirely separate universes, the interpretations of parallel universes are as diverse as they are mind-bending. But one question remains: if these universes exist, is there any way we can connect with them, or even prove they're real? So, if parallel universes exist, what does that mean for us? It's not just a scientific puzzle, it's a question that shakes the very foundation of how we see ourselves and our place in the cosmos. Let's start with the philosophical implications. If there are infinite versions of reality, then who are you really? Are you just one version of an infinite set of possibilities? It's a deeply unsettling idea. For centuries, philosophers have grappled with questions about identity, free will, and purpose. But the notion of parallel universes takes those questions to a whole new level. Think about it. In one universe, you might make a decision that leads to incredible success. In another, you might fail spectacularly. Does that mean your choices don't matter? Or does it mean every choice matters, because each one creates a new reality? And then there's the question of fate and free will. If parallel universes exist, does that mean every possible version of your life is already out there predetermined? Or are you still in control of your destiny, shaping one path while others unfold elsewhere? It's a paradox that challenges everything we think we know about how the universe works and how we work within it. Now let's shift gears to the scientific implications. The idea of parallel universes isn't just philosophical speculation. It emerges from some of the most cutting-edge theories in physics. For example, the many worlds interpretation of quantum mechanics suggests that every time a quantum event occurs, the universe splits into multiple versions. In one version, the particle moves left, in another it moves right. This isn't just a thought experiment. It's a direct consequence of how quantum systems behave. And on a larger scale, there's the theory of cosmic inflation. According to this idea, our universe may be just one of countless others created during the rapid expansion of space after the Big Bang. Each universe could have its own unique physical laws, making our universe just a tiny speck in an unfathomably vast multiverse. But here's the kicker. If these parallel universes exist, how do we prove it? After all, they lie beyond the reach of our current technology and understanding. Yet, scientists continue to search for clues, subtle hints in the cosmic microwave background, patterns in the distribution of galaxies, or even phenomena we haven't yet discovered. So what does it mean to live in a universe where infinite possibilities exist, but we may never fully grasp them? Are we explorers of a vast unknown, or merely observers of a single, narrow thread? The implications are as profound as they are mysterious, forcing us to rethink not just what we know, but how we know it. Now, let's dig into the science, the hard evidence and the theories that bring the idea of parallel universes out of the realm of imagination and into the world of physics. One of the most fascinating scientific ideas tied to parallel universes comes from quantum mechanics, the branch of physics that deals with the tiniest building blocks of reality, particles like electrons and photons. At this microscopic scale, the universe doesn't behave in ways we're used to. Instead of being predictable, particles exist in a strange state of uncertainty. Here's where it gets really interesting. In 1957, physicist Hugh Everett proposed a radical idea known as the many worlds interpretation. He suggested that whenever a quantum event occurs, whenever a particle has to choose between different states, the universe splits. Each possible outcome happens, but in a different branch of reality. Think of it like this: you're standing at a crossroads, deciding whether to turn left or right. According to the many worlds interpretation, you turn left in one universe, and in another you turn right. Both decisions are real, they just happen in separate realities. This theory isn't just about choices, it's about everything. Every quantum decision creates a branching network of parallel universes, each one following a different path. It's like an endlessly expanding tree, where every split creates new realities. But here's the catch: if these universes exist, we can't interact with them. They're separate, like pages in a book that never overlap. This makes the many worlds interpretation both thrilling and frustrating. It offers a stunning explanation for quantum behavior, but leaves us questioning whether we'll ever know if these other worlds truly exist. Still, the theory has its supporters. Many physicists believe it solves some of the deepest mysteries of quantum mechanics. But it also raises profound questions about reality. If the universe is constantly splitting, then how do we define what's real? And if every possibility exists somewhere, does that mean nothing is truly unique, including you? The many worlds interpretation is just the beginning. To uncover even more about the science of parallel universes, we'll need to go beyond the quantum scale and into the vastness of the cosmos itself. If the many worlds interpretation explores the smallest scales of reality, cosmic inflation takes us to the largest, the very origins of the universe itself. This theory not only explains how our universe came to be, but it might also suggest the existence of countless others. So, what is cosmic inflation? Imagine the universe as we know it, a vast expanse filled with galaxies, stars, and planets. Now, rewind time. About 13.8 billion years ago, everything we see today was packed into an unimaginably small, hot, and dense point. Then, in a fraction of a second, something extraordinary happened. The universe underwent a rapid, almost explosive expansion. This is what scientists call inflation. But here's where it gets fascinating. Many physicists believe that this process didn't just create our universe. Instead, inflation might have been happening everywhere, creating countless bubble-like universes, each expanding and evolving independently. Picture a pot of boiling water with bubbles forming, growing and floating away. Each bubble is its own universe with its own unique physical properties and laws of nature. This means that our universe might be just one bubble in an endless multiverse, a vast cosmic foam where universes are born and die. And here's the truly mind-bending part. In some of these universes, the laws of physics could be completely different. Perhaps gravity is stronger. Maybe stars never form. Or maybe life evolves in ways we can't even imagine. The idea of a multiverse emerging from cosmic inflation isn't just theoretical. Some scientists are actively searching for evidence. For instance, if our universe ever collided with another bubble universe in the distant past, it could leave subtle imprints in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. But even without direct proof, cosmic inflation offers an elegant explanation for why our universe looks the way it does. It might not just be a fluke. Instead, we could be one of countless universes, each with its own story, its own reality. So what does this mean for us? If the multiverse exists, then everything we know, our galaxy, our planet, even ourselves, might be just one tiny piece of an incomprehensibly vast puzzle. And that's both humbling and exhilarating. But the search for evidence continues. Could we ever find direct proof of other universes? Or will they remain forever beyond our reach, hidden in the depths of an infinite multiverse? If parallel universes exist, how would we ever prove it? Scientists are exploring some of the most ancient clues in the cosmos, remnants from the early universe itself, to find answers. These observations might hold the key to unlocking the mystery of the multiverse. Let's start with the cosmic microwave background, or CMB. This faint glow of radiation is like a time capsule, a snapshot of the universe just 380,000 years after the Big Bang. It's the oldest light we can observe, and it holds a wealth of information about how our universe began. When scientists study the CMB, they look for patterns, subtle irregularities in this ancient light. These patterns tell us how matter was distributed in the early universe and how galaxies eventually formed. But here's the intriguing part. If our universe ever interacted with another universe, perhaps a neighboring bubble in the multiverse, it could have left a detectable mark in the CMB. Imagine two soap bubbles colliding. The point of contact creates a ripple. Similarly, a collision between universes might have left imprints in the fabric of space-time that we could still see today. So far, no conclusive evidence of such collisions has been found, but that hasn't stopped scientists from looking. Telescopes like the Planck satellite have mapped the CMB in exquisite detail, searching for anomalies that could hint at a multiverse. Another area of exploration comes from the distribution of matter in the universe. If parallel universes exist, they might subtly influence how galaxies are arranged on the largest scales. Some researchers have suggested that strange alignments or patterns in the cosmos could be the result of interactions with other universes. And then there's the concept of quantum fluctuations. These tiny variations in energy, present during the inflationary period, could have seeded the creation of not just galaxies but entire universes. Observing these fluctuations and understanding their role might provide further clues about the multiverse. But here's the challenge. Proving the existence of other universes is incredibly difficult. By definition, these universes exist outside our own, beyond the boundaries of what we can directly observe. It's like trying to see the other side of a wall when you're locked in a room. Still, the search continues. Scientists are pushing the limits of technology and theory, probing deeper into the origins of our universe. Every discovery brings us closer to understanding whether we're part of a multiverse or whether our universe stands alone in the vast expanse of reality. So, could the answers be hidden in the light from the earliest moments of creation? Or will the multiverse remain forever a tantalizing mystery, just out of reach? Now, let's step away from the theories for a moment and dive into something more imaginative. What would it actually be like to live in a parallel universe? Could it feel similar to our own reality, or would it be so different that we wouldn't even recognize it as life? Picture this: you wake up one morning in a parallel universe. At first glance, everything looks the same. The sky is blue, the trees sway in the wind, and the familiar buzz of life fills the air. But as you step outside, small details start to shift. Maybe the cars hover instead of drive. Perhaps the laws of physics allow people to float rather than walk. Or maybe history unfolded differently. Your city, your country, even your own life took a drastically different path. Now imagine another version, one where the differences are subtle. Maybe you're living the same life, but with a few twists. You took a different career, married someone else, or pursued a long-forgotten dream. In a parallel universe, every decision, every chance encounter could lead to an entirely new reality. But what if the differences were more profound? In some universes, the laws of nature themselves could be entirely alien. Stars might never form, planets might not exist, time could flow backward, or gravity could be so weak that nothing holds together. Would such a universe even feel like reality to us? Here's a mind-bending thought. If we were to somehow find ourselves in a parallel universe, would we even know? Our senses and brains are adapted to perceive the reality we live in. A universe with radically different laws of nature might be completely incomprehensible, like trying to imagine a color you've never seen. But the biggest question is perhaps this: in a world of infinite possibilities, how much would those differences actually matter? Would you still be you in another universe? Or would the subtle changes in your environment, your choices, and your circumstances create someone entirely new? Exploring what it's like to live in a parallel universe forces us to reflect on what defines reality and what defines us. Is it our surroundings, our experiences, or something deeper that transcends all possible worlds? And yet, there's one more tantalizing question. If these universes are out there, could we ever visit them? Could we cross the boundaries of our reality and step into another? That's what we'll explore next. Now comes the big question, the one that feels like it's straight out of science fiction. Could we ever travel to other realities? Could we leave our universe and step into a parallel one? To answer that, we need to start by understanding the boundaries of our own universe. Right now, everything we know about space, time, and matter suggests that our universe is a closed system. Like living inside a snow globe, we're confined to the dimensions and physical laws that define our reality. So the idea of breaking out and entering another universe seems impossible. But impossible is a word that science loves to challenge. Some theories suggest there might be loopholes in the fabric of space-time, portals, if you will, that could allow travel between universes. Think of wormholes, those hypothetical tunnels connecting distant parts of space. Some scientists believe that if wormholes exist, they might also act as bridges between entirely different realities. Here's the catch: wormholes, if they exist at all, would be incredibly unstable. The tiniest disturbance could cause them to collapse before anyone or anything could pass through. But what if we could stabilize one? Theoretically, advanced civilizations, far more advanced than ours, might have the technology to harness wormholes as gateways to other universes. And then there's the idea of quantum entanglement, a strange phenomenon where two particles, no matter how far apart, are mysteriously connected. Some physicists speculate that this spooky action at a distance might hint at deeper connections between universes. Could quantum mechanics provide a roadmap for traveling between realities? Of course, there are massive challenges. Even if we discovered a way to reach another universe, we'd have no idea what conditions await us. Would it be safe? Would the laws of physics there even allow us to survive? Imagine stepping into a universe where gravity is so strong that you're instantly crushed, or so weak that atoms can't hold together. But there's another question, perhaps a more philosophical one. If we could travel to other realities, should we? What happens if we encounter another version of ourselves? What ethical dilemmas arise from meddling in a universe that isn't ours? For now, the idea of traveling to parallel universes remains a tantalizing dream, a frontier for future scientists and explorers to imagine. But even if we can't cross the boundaries of our reality, the very act of asking these questions pushes the limits of our understanding and inspires us to think beyond what we know. So, will we ever build a bridge to another universe? Or will the multiverse remain forever out of reach, a world of infinite possibilities just beyond the edge of our imagination? Now, let's confront one of the most profound questions about parallel universes. What happens if we interact with another version of ourselves? It's an idea that feels exciting and unsettling all at once, raising ethical and philosophical dilemmas that challenge how we see ourselves and our place in reality. Imagine meeting another you. At first, it might feel like looking into a mirror, but this reflection isn't exact. Maybe they made different choices. Maybe they're living the life you always dreamed of, or the one you feared. How would that change the way you see yourself? Would you envy them? Pity them? Or would you feel a sense of connection, knowing that their life could so easily have been yours? Here's the ethical dilemma. Would you have the right to influence their reality? If their life is better, would you try to learn from them, or even take their place? If it's worse, would you feel obligated to help them, even if it meant disrupting their world? And what about the consequences of your interaction? Think about the ripple effect. In your universe, every choice you make affects the people around you. But in a parallel universe, the stakes could be even higher. A small action, one conversation, one decision, might radically alter an entire timeline. Then there's the question of identity. If there are infinite versions of you, is there such a thing as the real you? Are you defined by your choices, your circumstances, or something deeper, something constant across all realities? This isn't just a philosophical exercise, it's a question that strikes at the core of how we understand ourselves. And finally, the most unsettling question of all, what if the other version of you is fundamentally different? What if they've made choices that you can't reconcile with, choices that challenge your sense of morality or identity? Could you still see them as you, or would they feel like a stranger? Interacting with another version of ourselves isn't just a fascinating what if. It forces us to confront the nature of free will, morality, and selfhood. It's a thought experiment that asks, if we are one of infinite possibilities, how much of who we are is truly unique? Perhaps the ultimate ethical question is this: if we ever had the chance to step into another version of our life, would we take it? Or would the risks to ourselves, to others, and to reality itself be too great? The idea of parallel universes isn't just a scientific or philosophical concept. It's a profound challenge to how we perceive reality and our place within it. For centuries, humanity has sought to understand the cosmos, from ancient myths about the heavens to the modern equations of physics. We've long assumed that our universe is all there is, that everything we know and experience exists within this singular reality. But the possibility of parallel universes forces us to confront an unsettling truth. What if we're just a tiny piece of something infinitely larger? Think about it. If there are countless other universes, each with its own stars, galaxies, and perhaps even life, then our universe, our home, might not be as unique as we once thought. That realization can feel humbling, even disorienting. Are we just one story among billions, playing out in an endless cosmic library? And what about you? If infinite versions of you exist, each shaped by slightly different choices or circumstances, then what defines your individuality? Are you truly unique, or just one expression of endless possibilities? This idea doesn't just challenge how we see ourselves, it also forces us to rethink humanity's place in the grand scheme of things. For generations, we've seen ourselves as the center of the story, the observers of the universe. But if the multiverse exists, then we're not the center at all. We're a single thread in a vast, intricate tapestry, woven alongside infinite others. But here's the paradox. While the concept of parallel universes can make us feel small, it can also inspire a profound sense of connection. If reality is infinite, then every choice, every possibility, every moment has value. It's a reminder that, even in the vastness of the cosmos, our actions still matter, because they're part of something much greater than ourselves. The idea of parallel universes isn't just about what's out there, it's about how we understand our place in it. Are we explorers, seeking answers to the ultimate mysteries? Or are we simply participants in a story so vast and complex that we may never fully comprehend it? Either way, it's a journey that forces us to see reality and ourselves in a whole new light. The concept of parallel universes doesn't just expand our view of the cosmos. It directly challenges some of our most deeply held beliefs about free will, fate, and the nature of consciousness. Let's start with free will. We like to think of our choices as defining who we are. Every decision, big or small, feels like a unique thread in the fabric of our lives. But what if, in the multiverse, every choice you could possibly make does happen? In one universe you chose one path, in another a completely different one. If every possibility is realized somewhere, then do you truly have free will? Or are you just playing out one version of an endless set of possibilities? Then there's fate. If parallel universes exist, does that mean everything is inevitable? If every outcome exists in some reality, then does it matter which choices you make? Or does the existence of infinite possibilities mean that no single outcome is destined? It's a paradox that forces us to rethink what it means to be in control of our lives, and whether the idea of control itself even makes sense in a multiverse. And what about consciousness? Who are you in the context of infinite versions of yourself? Is your consciousness unique to this universe, or is it somehow connected to all your counterparts in other realities? Philosophers and scientists have long debated whether consciousness is a purely physical phenomenon or something more profound. The multiverse takes this debate to a new level. Could our minds, our very sense of self, be just one fragment of a larger, interconnected whole? Here's a thought experiment. If you could observe every version of yourself across all universes, would you still feel like the same person? Or would the differences, subtle or dramatic, redefine your understanding of who you are? The idea of parallel universes doesn't just stretch the boundaries of science. It forces us to confront some of the most profound questions about existence itself. It challenges the very concepts of individuality, choice, and identity, leaving us to wonder, in a reality of infinite possibilities, what does it truly mean to be? These are not easy questions to answer, but they remind us that exploring the multiverse isn't just a journey through space and time, it's a journey into the depths of our own understanding, one that may forever change the way we see ourselves and the universe around us. Parallel universes don't just challenge our understanding of reality, they open the door to entirely new realms of discovery. If even a fraction of the multiverse theories prove true, they could revolutionize the way we see the cosmos and our place within it. Imagine the possibilities. If we could uncover evidence of other universes, we might learn why our universe has the specific properties it does, why the laws of physics are fine-tuned to allow stars to form, planets to exist, and life to evolve. Perhaps, in studying other realities, we'd find universes where the conditions are wildly different, teaching us more about the delicate balance that makes our own universe so special. And what about the origins of reality itself? Parallel universes could provide clues about how and why the universe began. Some scientists propose that studying the multiverse might reveal whether the Big Bang was a singular event or just one of countless beginnings in an endless cycle of cosmic creation. Then there's the technological potential. If we could somehow harness the principles of parallel universes, like the mysterious connections hinted at by quantum mechanics, imagine what might be possible. Could we use those principles to solve problems we've never been able to solve before, like faster-than-light travel, infinite energy sources, or even new ways to explore the cosmos? But perhaps the greatest discoveries would come not from the differences between universes, but from what they share. By studying the multiverse, we might uncover universal truths, patterns or principles that apply across every reality. These insights could help us better understand the deepest questions about existence, why there is something rather than nothing, what consciousness truly is, and what the ultimate fate of reality might be. Of course, these discoveries are still far off, lying on the very edges of what we can imagine, but the potential is breathtaking. The multiverse, if real, doesn't just expand the cosmos, it expands the boundaries of human knowledge, inviting us to explore not just the universe we live in, but the infinite possibilities that lie beyond. Ultimately, the pursuit of understanding parallel universes isn't just about science, it's about curiosity. It's about the human drive to seek answers to the biggest questions, to push past the limits of what we know, and to embrace the unknown with open minds and boundless wonder. The discoveries we make might not just change what we know about the universe, they might change what we know about ourselves. The possibility of parallel universes is more than just a scientific theory or a philosophical idea. It's an invitation to expand our imagination and challenge the way we see reality. Few concepts are as captivating or thought-provoking, drawing us into questions that seem to stretch beyond the limits of what we can understand. If these universes exist, they offer a glimpse into infinite possibilities, worlds where history unfolded differently, where the laws of physics may not resemble our own, or where versions of ourselves are living lives we can only dream of. But even if parallel universes remain forever out of reach, the very act of exploring them forces us to think bigger, to ask questions that transcend the boundaries of science and philosophy. At its core, the idea of parallel universes reminds us of the vastness of reality. It's humbling to imagine that our universe might be just one small piece of an endless multiverse, and yet it's exhilarating to know that we're part of something so immense, so mysterious, and so beautiful. And perhaps, whether or not we ever find proof of other realities, the most important discovery might be what this exploration teaches us about ourselves, about our place in the cosmos, about the choices we make, and about the boundless curiosity that drives us to keep asking, keep searching, and keep wondering. So, as we close this journey, consider this. In a universe so full of mystery, where every possibility could exist somewhere, what does that mean for the choices you make today? What does it mean for how you see yourself, your world, and the infinite unknown? The answers may lie beyond our reach, but the questions will always push us forward. So, as you step back into your own universe, carry this thought with you. Every question we ask, every possibility we imagine, brings us closer to understanding the extraordinary reality we call home. And who knows? Perhaps, somewhere in another reality, another version of you is asking these very same questions, dreaming, exploring, and seeking answers in their own way. Now, let's explore the next mind-bending concept. Quantum mechanics. This theory explains the behavior of particles at microscopic scales, where classical physics no longer applies. Quantum mechanics introduces us to a world governed by probabilities, uncertainties, and phenomena that challenge our understanding of reality. One of the cornerstones of quantum mechanics is wave-particle duality, which suggests that particles like electrons and photons can behave both as particles and as waves. In the classic double-slit experiment, particles fired at a barrier with two slits create an interference pattern, behaving like waves. However, if we observe which slit each particle passes through, they act like particles again, as though the act of measurement changes their behavior. This mysterious link between observation and reality questions the very nature of existence. Next, we have the uncertainty principle, proposed by Werner Heisenberg in 1927. It states that we can't know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't due to measurement limitations, but is a fundamental property of quantum particles, adding an element of randomness and unpredictability to the quantum world. Imagine you have a ball moving along a path. In classical physics, you can measure both its speed and position accurately. However, in quantum mechanics, if you try to measure an electron's exact position, you inherently alter its momentum, making precise measurement impossible. Quantum superposition takes uncertainty a step further. It states that particles can exist in multiple states simultaneously until observed. Erwin Schrödinger famously illustrated this with a thought experiment, Schrödinger's cat. Imagine a cat in a sealed box with a vial of poison. If a radioactive atom decays, the vial breaks, killing the cat. Until we open the box, the cat is in a superposition of being both alive and dead. This paradox highlights how observation affects outcomes in the quantum world. Superposition has practical applications, especially in quantum computing. Quantum computers utilize qubits, which can exist in multiple states at once, allowing them to perform vast amounts of calculations simultaneously. This gives quantum computers the potential to solve complex problems far beyond the reach of classical computers. Quantum entanglement is one of quantum mechanics' strangest phenomena. When particles become entangled, the state of one instantaneously affects the state of the other, no matter the distance. If we measure one particle, we instantly know the state of the other, even if they're light years apart. This phenomenon, called spooky action at a distance by Einstein, challenges the idea that objects are only influenced by their immediate surroundings. Entanglement has significant implications for quantum communication and cryptography. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems exist in superposition until observed, causing them to collapse into one definite state. This raises profound questions. Does reality depend on consciousness? If observing a particle can change its state, what role does our mind play in shaping the physical world? This interpretation bridges physics with philosophical debates about the nature of reality. In contrast to the Copenhagen interpretation, the many worlds interpretation proposes that all possible outcomes of a quantum event actually occur, each in a separate universe. For example, in Schrödinger's cat experiment, one universe would have a live cat and another would have a dead one. The many worlds interpretation implies a multiverse of branching realities, each representing different outcomes, avoiding the need for wave function collapse. While it sounds like science fiction, this interpretation has gained popularity among physicists. Quantum mechanics has led to groundbreaking advancements in technology, especially in computing, cryptography, and telecommunications. Quantum computers, for example, use qubits that can represent both 0 and 1 simultaneously, enabling them to solve complex problems much faster than classical computers. Quantum cryptography uses entanglement to develop unbreakable encryption methods. Quantum teleportation, although not teleportation in the science fiction sense, uses entanglement to instantly transfer information, potentially revolutionizing secure communications. Quantum mechanics presents philosophical and scientific challenges that stretch beyond physics. Unlike the deterministic world of classical physics, the quantum world introduces probabilities, where outcomes depend on observation, challenging ideas of objective reality. Quantum mechanics has inspired numerous interpretations and debates. Is reality independent of observation, or does our consciousness shape it? These questions bridge the realms of science and philosophy, making quantum mechanics one of the most existentially provocative theories. To summarize, quantum mechanics defies conventional understanding with concepts like wave-particle duality, uncertainty, superposition, and entanglement. This theory challenges classical physics, introducing a probabilistic and interconnected universe that pushes the boundaries of what we know. Quantum mechanics has paved the way for technological breakthroughs in computing and cryptography, yet leaves us questioning the nature of reality itself. As we journey deeper into these mysteries, quantum mechanics will continue to shape our understanding of the universe and invite us to rethink reality. Let's move on to string theory, an ambitious and mathematically complex theory that aims to unify all of the fundamental forces in nature and provide a theory of everything. String theory suggests that the fundamental building blocks of the universe aren't particles like electrons or quarks, but incredibly tiny, vibrating strings. These strings and their vibrations supposedly give rise to all particles and forces, making string theory one of the most promising yet confusing approaches in modern physics. At its core, string theory proposes that the building blocks of our universe are one-dimensional strings. Each string vibrates at a specific frequency, producing different particles and forces, similar to musical notes on a string instrument. For example, an electron and a photon would both be different vibrational patterns of a fundamental string, much like different notes produced by the same string on a musical instrument. One of the revolutionary aspects of string theory is its potential to unify quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. While quantum mechanics explains the behavior of particles and relativity explains gravity, these two frameworks are currently incompatible. String theory could provide a way to reconcile them by offering a single, coherent framework that accounts for all known forces and particles. Multiple versions of string theory emerged in the 1980s, leading to confusion. However, physicist Edward Witten introduced M-theory, uniting these versions into one overarching framework. M-theory suggests that strings may not be the only fundamental structures. Higher dimensional objects called branes, short for membranes, might also exist. These branes could be as small as a single point or as vast as a universe, adding a whole new layer of complexity to the theory. According to M-theory, Our own universe might be a three-dimensional brain floating within a higher dimensional space, possibly interacting with other brains and universes. One of the most challenging and mind-bending aspects of string theory is its requirement for additional spatial dimensions. In everyday life, we experience 3 dimensions of space and 1 dimension of time. However, for string theory's equations to work, 10 or even 11 dimensions are required. The additional dimensions in string theory are hypothesized to be compactified or curled up so small that we can't perceive them. Imagine a 2-dimensional sheet of paper curled into a tight spiral. If you zoomed out far enough, it would appear as a 1-dimensional line. In a similar way, the extra dimensions in string theory could be curled up to scales smaller than an atom, making them invisible to us. The idea of extra dimensions, while mathematically sound, is almost impossible to visualize, adding to the confusion and intrigue surrounding string theory. These dimensions could hold the key to understanding forces that seem weak or mysterious in our familiar dimensions, such as gravity. Because string theory allows for many possible solutions, there may be an enormous number of vacua or possible configurations of the universe. Each configuration would correspond to a different set of physical laws and constants, leading to the possibility of a multiverse, an immense collection of universes, each with its own distinct properties. In other words, our universe could be one among countless others, each governed by different rules. This idea is both intriguing and problematic. If the multiverse is real, it would be impossible to test or observe directly, meaning we may never confirm or falsify its existence. Critics argue that this makes string theory difficult to treat as a true scientific theory, as it may lead to predictions that cannot be tested or observed. Despite its promise, string theory faces challenges. It lacks testable predictions, is mathematically complex, and some question if it qualifies as a scientific theory due to its non-falsifiable nature. Even without concrete proof, string theory has profoundly impacted physics and mathematics. Concepts from string theory have influenced quantum field theory and pure mathematics, leading to insights that extend beyond its original scope. Physicists continue refining string theory, hoping that future experiments or new technology will reveal supporting evidence. String theory offers a path to unify all fundamental forces, potentially revealing a theory of everything. Whether it leads to a revolutionary understanding or paves the way for future theories, string theory marks a bold step in our quest to unravel the cosmos mysteries. From Einstein's theory of relativity to the mind-bending mysteries of quantum mechanics. From the explosive origins of the Big Bang to the eerie invisibility of dark matter, these ideas are not just theories. They're gateways to a universe beyond imagination. But what if there's more? What if our universe is just one of many? Or brace yourself, what if we're all living in a simulation? Embark with us on a journey to uncover the universe's greatest mysteries, diving into mind-bending theories that will expand your imagination. Together, we'll travel through the cosmos, unlocking the secrets of existence. Theory of relativity. Developed by Albert Einstein in the early 20th century, this theory reshaped our understanding of space, time, and gravity. It's divided into 2 parts: general relativity and special relativity, each revealing unique insights about the universe that continue to shape science today. Let's dive into general relativity, introduced by Einstein in 1915. Unlike earlier concepts of gravity as a force acting across space, general relativity describes gravity as a result of curvature in the fabric of space-time. Picture a stretched-out trampoline with a heavy ball in the center. The weight of the ball creates a dip, causing smaller objects to move toward it. In the same way, massive objects like stars and planets create similar dips in space-time, which draws other objects toward them. This is how general relativity redefines gravity as the bending of space and time itself. This idea of space-time as a 4-dimensional entity where mass and energy can cause a curvature was groundbreaking. The closer an object is to a massive body, such as a planet or a star, the stronger the gravitational effect it feels due to this curvature. In 1919, general relativity received its first experimental confirmation during a solar eclipse. Astronomers observed that starlight passing close to the sun was bent, just as Einstein had predicted. This phenomenon, known as gravitational lensing, occurs because massive objects, like the sun, bend the space around them, causing light to follow a curved path. Today, gravitational lensing remains a valuable tool in astronomy, allowing scientists to study distant galaxies and even detect objects that would otherwise be invisible. The implications of space-time curvature are profound. For example, in areas where mass is exceptionally dense, such as in black holes, space-time curvature becomes so intense that it collapses into what's known as a singularity, where gravitational forces become infinitely strong. At a singularity, the known laws of physics break down, creating an area where even time may cease to exist as we understand it. Einstein's equations in general relativity also hinted that the universe could not be static, eventually leading scientists to discover the expansion of the universe and support for the Big Bang theory. This concept is foundational in cosmology and helps us understand the vast structure of the universe. Moving to special relativity, which Einstein introduced in 1905, we encounter another revolutionary idea. The speed of light is constant, regardless of the motion of the observer or the light source. Special relativity specifically applies to objects moving at constant, non-accelerating speeds and fundamentally changes how we understand time and space. According to this theory, as an object nears the speed of light, time slows down for it relative to an outside observer. This phenomenon, called time dilation, has been observed in experiments where fast-moving particles and clocks flown around Earth experience measurable time differences. For example, GPS satellites in orbit need corrections for time dilation to maintain accurate navigation on Earth. Two critical concepts arise from special relativity: time dilation and length contraction. Time dilation means that time slows down for objects moving at high speeds. This could theoretically allow for long-distance space travel, where astronauts could experience only a few months while years pass on Earth. Length contraction, on the other hand, states that objects in motion appear shorter in the direction they are moving. This effect is only noticeable at speeds close to the speed of light, making interstellar distances appear shorter for high-speed travelers. Together, these concepts reshape our understanding of time, space, and even the feasibility of human space exploration. One of the most famous outcomes of special relativity is the equation E equals mc squared, which reveals that energy is equal to mass times the speed of light squared. This equation implies that mass and energy are interchangeable, meaning that even a small amount of mass can release a tremendous amount of energy. This principle forms the foundation of nuclear energy and explains why stars emit so much light and heat through nuclear fusion. In nuclear reactions, tiny amounts of matter are transformed into vast quantities of energy. This equation also led to predictions about antimatter and other exotic forms of matter, enriching our understanding of particle physics and cosmology. Despite its success, relativity isn't without challenges. General relativity, which describes large-scale phenomena like stars and galaxies, doesn't align well with quantum mechanics, which governs atomic and subatomic particles. The pursuit of a unified theory that combines both realms, often called the theory of everything, is one of the biggest goals in theoretical physics, with approaches like quantum gravity and string theory attempting to bridge this gap. Furthermore, general relativity's predictions about black holes and singularities hint that our understanding of space-time might still be incomplete. Observations of phenomena like dark energy, which accelerates the universe's expansion, suggest there are aspects of physics yet to be discovered. Though it may seem abstract, relativity has practical applications in everyday life. For instance, the Global Positioning System, GPS, relies on relativity-based adjustments, as satellites orbiting Earth experience different gravitational and speed effects on time. Without these adjustments, GPS accuracy would quickly degrade. Relativity also plays a crucial role in particle accelerators, which must account for relativistic effects as particles approach light speed. The Large Hadron Collider, for example, uses these principles to ensure the accuracy of high-energy particle physics experiments. In summary, The theory of relativity transformed how we perceive the universe by demonstrating that space and time are interconnected and can be influenced by gravity and motion. General relativity redefined gravity through space-time curvature, while special relativity reshaped our understanding of time, speed, and energy. Together, these theories form the backbone of modern physics and continue to inspire new technological and scientific advancements. But relativity is only the beginning. As we venture further into the mysteries of black holes, time travel, and the expanding universe, we may yet uncover even more mind-bending truths about reality. Have you ever looked up at the night sky and wondered about the secrets it holds deep within its starlit expanse? What mysteries lie beyond the reaches of our sight, waiting to be discovered? Welcome to Unlocking the Universe. 10 mind-blowing cosmic mysteries. In today's journey, we're diving into some of the most astonishing and perplexing facts about the cosmos. From the mind-bending reality of black holes to the enigmatic forces of dark matter and dark energy, the universe is far more mysterious and incredible than we could have ever imagined. So buckle up as we explore these cosmic wonders and unravel the mysteries of the universe one fact at a time. Fact 1. The size of the observable universe. Imagine trying to comprehend the full scope of where we are. It's a challenge that stretches the limits of our minds. The observable universe, the part of the cosmos we can theoretically see from Earth, spans about 93 billion light-years in diameter. But what does that really mean? A light-year is the distance light travels in 1 year, nearly 6 trillion miles. Now, multiply that by 93 billion, and you're just starting to scratch the surface of the sheer scale of our universe. Within this unimaginable expanse, there are at least 2 trillion galaxies, each brimming with millions to trillions of stars, and even more planets. Each light year, each galaxy, represents a part of the universe full of mysteries yet to be explored. And as vast as the observable universe is, what lies beyond is even more intriguing. Because of the finite speed of light and the age of the universe, we can only see as far as light has had time to travel since the Big Bang. What exists beyond this cosmic horizon remains one of the greatest questions in astronomy. Fact 2. Black holes. These are some of the most mysterious and powerful entities in the universe. A black hole is a point in space where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. Most black holes form from the remnants of a large star that dies in a supernova explosion. When the star's core collapses under the weight of its own gravity, it can compress to a point, creating a black hole. In 2019, humanity got its first ever look at a black hole's event horizon, thanks to the Event Horizon Telescope. This image captured a black hole at the center of the galaxy M87, revealing the shadow of the black hole surrounded by a bright glowing ring of light, bending due to its immense gravity. The gravity of a black hole is so strong that it distorts space and time around it. If you were to approach a black hole, you would experience something known as spaghettification, where you'd be stretched into a thin strand of matter due to the gravitational forces. Our very own Milky Way galaxy harbors a supermassive black hole at its center, known as Sagittarius A. Supermassive black holes like this one might play a key role in how galaxies form and evolve over billions of years. Fact 3. Dark matter and dark energy. Though we can see stars, planets, galaxies, and even the light from distant cosmic events, these account for only about 5% of the universe. The rest is made up of dark matter and dark energy, which together compose about 95% of the total mass and energy of the cosmos. Dark matter, making up about 27% of the universe, does not emit, absorb, or reflect light. It neither glows nor can be directly observed, yet we know it exists because of the gravitational effects it has on the visible matter around it. This mysterious substance binds galaxies together and is essential for the structure of the universe. The remaining 68% is dark energy, an even more mysterious force that is driving the accelerated expansion of the universe. Unlike anything else we know, dark energy appears to be a property of space itself. Since the Big Bang, the universe has been expanding, but thanks to dark energy, this expansion is not slowing down as previously thought, it's speeding up. This discovery in the late 1990s has transformed our understanding of the cosmos and its future. The enigmatic nature of dark energy poses one of the biggest questions in science. What is its true nature, and what does it mean for the fate of the universe? Will the universe continue to expand indefinitely, tear itself apart, or eventually stop expanding? Fact 4. The multiverse theory. While our universe is vast beyond comprehension, it might not be the only one. According to the multiverse theory, what we have traditionally called the universe could be just one of countless others in a grander multiverse. This theory extends from ideas in physics that suggest possible multiple universes may arise from the same quantum fluctuations that inflated our own universe. These universes might vary dramatically in their laws of physics, their configurations of matter, and even their fundamental constants. One intriguing version of the multiverse is the many worlds interpretation of quantum mechanics, where every decision creates a new split in reality, leading to new universes for each possibility. Imagine a universe where dinosaurs never went extinct, or where gravity is not a fundamental force. Theoretical frameworks like string theory and cosmic inflation provide some support for the multiverse concept, suggesting that the cosmos might consist of multiple dimensions beyond our familiar three-dimensional space. Each of these dimensions could potentially be a separate universe. The idea of a multiverse pushes the boundaries of our understanding and challenges the very notion of reality. It raises profound questions. If other universes exist, could we ever detect them? And what would this mean for our understanding of existence itself? Fact 5. Neutron stars. Among the universe's most extreme objects, neutron stars are the dense remnants of massive stars that exploded in supernovae. Despite their small size, typically about 20 kilometers in diameter, these stars pack a staggering amount of mass. Imagine the mass of the Sun, over 1 million times the mass of the Earth, compressed into a sphere just 12 miles across. The result is a material so dense that a single teaspoon of neutron star matter would weigh about 6 billion tons. That's equivalent to the combined weight of all humans on Earth. Neutron stars are fascinating not only because of their density, but also their rapid rotation and strong magnetic fields. Some neutron stars spin hundreds of times per second. These stars can also appear as pulsars, which are neutron stars that emit beams of electromagnetic radiation. These beams are only visible when they sweep across the Earth, similar to the light from a lighthouse. Pulsars are so precise in their rotation that astronomers use them as cosmic clocks. Some neutron stars are known as magnetars, which have the most powerful magnetic fields in the universe. These fields are so intense that they can cause starquakes and emit giant flares of energy, which can disrupt satellites and create spectacular light shows in the sky. Fact 6. The expanding universe. Since the dawn of the 20th century, astronomers have understood that the universe is expanding. This was first proposed by Belgian priest and astronomer Georges Lemaitre, and later confirmed by Edwin Hubble, who observed that distant galaxies are moving away from us in every direction. What's fascinating is that it's not just the galaxies moving through space. The fabric of space itself is expanding. This means that, with each passing second, every part of the universe is getting slightly further away from every other part. Scientists measure this expansion using something called redshift. As light from distant galaxies reaches us, it shifts to longer, redder wavelengths as space expands. This shift provides crucial information about the speed of the galaxy's recession due to the universe's expansion. These 6 cubes show the simulated distribution of galaxies at redshifts 9, 7, 5, 3, 2, and 1, with the corresponding cosmic ages shown. As the universe expands, the density of galaxies within each cube decreases, from more than 500,000 at top, left to about 80 at lower right. Each cube is about 100 million light-years across. Galaxies assembled along vast strands of gas separated by large voids, a foam-like structure echoed in the present-day universe, on large cosmic scales. This visualization shows the number and clustering of simulated galaxies at different cosmic ages, ranging from 4% to 43% of the universe's current age of 13.8 billion years. Each cube represents a fixed volume of space about 100 million light-years per side. Over the sequence, the expansion of the universe quickly lowers the density of galaxies. Each cube shows a specific cosmological redshift, from 9 to 1, with earlier cubes cast in redder shades. Recent discoveries have revealed that the universe is not just expanding, but it's accelerating. This acceleration is thought to be driven by dark energy, an unknown form of energy that makes up about 68% of the universe. The implications of this expanding universe are profound. If the expansion continues indefinitely, the future of the cosmos could be a big freeze, where galaxies eventually drift so far apart that the stars burn out, leaving a cold, dark universe. Fact 7. The cosmic microwave background. Discovered quite by accident in 1964, the cosmic microwave background, or CMB, is a faint glow of light that fills the entire universe. It is the afterglow, radiation, left over from the Big Bang, and it provides us with a snapshot of the infant universe just 380,000 years after its inception. This cosmic relic was stumbled upon by Arno Penzias and Robert Wilson, who initially mistook it for noise from pigeons in their antenna. Their discovery provided strong evidence for the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB is not perfectly uniform. It contains tiny temperature fluctuations that represent the seeds of all future structure, the galaxies, clusters, and vast voids that would eventually form. By studying these patterns, cosmologists can learn about the composition and evolution of the universe. At the time the CMB was emitted, the universe had cooled enough for electrons and protons to combine into neutral atoms, making the universe transparent to radiation for the first time. This moment is known as recombination. Today, advanced satellites and observatories continue to study the CMB to glean more insights into the universe's rate of expansion, the nature of dark energy, and even hints about inflation, a theorized exponential expansion of the early universe that would have happened a fraction of a second after the Big Bang. Fact 8. Life's ingredients are cosmic. It's a humbling and fascinating fact that nearly all elements on Earth were formed in the heart of stars. This cosmic alchemy, where simple elements like hydrogen and helium are transformed into heavier elements, occurs under the extreme pressures and temperatures found in stars. Throughout their lifetime, stars fuse hydrogen into helium, helium into carbon, and so on, up to iron. But the creation of elements heavier than iron requires even more dramatic events, such as supernovae and the collision of neutron stars. When a massive star explodes in a supernova, it releases an immense amount of energy and spews newly formed elements into space. Even gold, platinum, and uranium are forged in these cosmic catastrophes and the cataclysmic mergers of neutron stars. These elements, scattered across the cosmos, eventually coalesce into new star systems and planets, including our own. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones all originated from stardust. So next time you look up at the night sky, remember that we are not just inhabitants of the universe, we are literally made of the universe. Every atom in your body was once part of a star far across the galaxy. We are, in the most literal sense, stardust. Fact 9. Exoplanets and the search for life. Since the confirmation of the first exoplanets in the 1990s, our understanding of the universe has expanded dramatically. To date, thousands of planets have been discovered orbiting stars outside our solar system. These exoplanets come in a fascinating array of sizes, compositions, and orbits. Among these, some are eerily similar to Earth, with conditions that may support life. Scientists use advanced telescopes like Kepler and test to detect these distant worlds by watching for the slight dimming of a star as a planet passes in front of it, a method known as the transit method. Particularly exciting are those exoplanets in the habitable zone, a region around a star where conditions might be right for liquid water, a crucial ingredient for life as we know it to exist on the surface. The quest to find extraterrestrial life is intensifying. Future missions plan to analyze the atmospheres of these exoplanets, searching for signs of life such as oxygen, ozone, and methane. Such discoveries could answer one of humanity's oldest questions: are we alone in the universe? Every new exoplanet discovered broadens our perspective, reminding us of the vast possibilities that lie beyond our home planet. As we continue to explore, we not only learn more about the universe, but also about the potential for life's diversity beyond Earth. Fact 10. The youngest galaxies. By peering deep into the cosmos, astronomers are not just looking out in space, they are also looking back in time. Using powerful telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, scientists have been able to observe galaxies as they existed just a few 100 million years after the Big Bang. These observations are crucial because they show us the earliest stages of galaxy formation. The youngest galaxies are often small, irregular, and highly active, quite different from the large, well-structured spiral and elliptical galaxies we see in the nearby universe. Studying these young galaxies helps us understand how galaxies grow and evolve. For instance, we see that early galaxies were often much more chaotic, with high rates of star formation and frequent collisions that eventually led to the large, organized structures of stars we are familiar with today. These galactic youths are not just random patches of stars, they are the building blocks of today's universe. Observing them offers clues about the fundamental processes that have shaped everything we see around us, from the distribution of galaxies to the very structure of the cosmos. As technology advances, we will continue to push the boundaries of what we can observe. Each new discovery not only helps us piece together the cosmic puzzle, but also connects us more deeply with the origins of our own galaxy and ultimately, our place in the universe. Thank you for joining me on this cosmic voyage. The universe is not just something out there, it's a part of us, and we continue to explore it. We learn more about ourselves. If you enjoyed this exploration, share your thoughts and questions in the comments below. What part of the universe fascinates you the most? Let's keep the conversation going. Don't forget to like, subscribe, and click the bell icon to receive updates on our latest videos. Together, let's continue to unlock the mysteries of the universe.